Welcome to the OK Let's Learn podcast. This is two podcasts in one. One where we dive into tons of interesting topics, and another where we dive into tons of interesting stories and books. My name is Kevin O'Keefe. So today, let's learn all about electricity, the invisible force that powers our world. You know it, you appreciate it, but do you understand it? Can you see it? No. It powers everything in our modern world. And for years, obviously it was out there, but we didn't understand it. We certainly couldn't harness it. So we're going to learn about what it is, where it comes from, how it gets to our house, the important people along the way in terms of its discoveries, in terms of how we could harness it and use it. And really, it's no question, it's got to be up there in terms of the most discoveries in human history. Is it physics or is it chemistry? The answer is pretty much both, right? Because if you think about it, it's actually part of physics because it deals with energy, it deals with forces and the behavior of these tiny particles. And of course, it's chemistry because it involves these tiny particles, right? There's chemical reactions inside batteries. There's electrons that move, and we'll get to these electrons because, there it is. Electricity, electrons. And would you guess where electrons, the word, comes from? Yeah, it comes from amber. Amber? What's that? All right, I'm getting ahead of myself. Here we go. 2,000 years ago, this is when the story starts. 600 BC, ancient Greeks noticed something strange. There was this philosopher by the name of Thales of Miletus. And you can go back all the way back to my episodes on ancient Greece with Alexander the Great. Yeah, they didn't have last names. It was like where you were from. So Thales, he rubbed a piece of amber with fur. After rubbing it, the amber could attract, like he noticed this like magic where feathers and bits of straws were literally attracted to it. Nobody understood why, but what they were seeing was static electricity. In fact, the Greek word for amber was electron, E-L-E-K-T-R-O-N. That word eventually gave us the modern word of electricity. But for 2,000 years, people knew that this force existed, but no one understood what it was. So what is it? And what was it? Oh, it's static electricity, right? Well, is that the same as the electricity that we're talking about when we plug something into the wall? Yes and no. It sounds confusing, but here's the easiest way to think about it. Water, puddle of water and flowing river, right? They're both water. Static electricity is like the puddle. And electrical power in your home, the electricity in our home is like the river. The same thing is involved, but one is sitting still and the other is moving. That's the example. That's the metaphor for comparing static electricity and regular electricity. We kind of refer to regular electricity as current electricity. So basically static electricity is this like buildup of electrical charges that all of a sudden, bang, it discharges in a single burst, whereas the current electricity is a continuous flow of electrical charges through a path to different power devices. But again, we're getting ahead of ourselves. We're starting here at static electricity because when we dive deep into what electricity is, this is the best starting point, right? At its absolute core, static electricity is the temporary imbalance of electrical charges on the surface of an object. To understand how this imbalance happens, we got to zoom all the way into the atoms. Everything around us is made up of atoms. Yeah, your hair, a balloon, a metal doorknob, are all made of atoms. And we're talking about each of these because you know where we're going. All these, we have connections to feeling electricity, right? That shock that we get. Well, inside all the atoms are something called protons and electrons. Protons are located in the center, the nucleus of the atom, and they hold a positive charge. They're locked tightly in place and can't move, right? Electrons, well, they're orbiting. They're going around the outside of the nucleus, and they hold a negative charge. And yeah, they're moving all the time. Normally, every atom has an equal number of protons and electrons. That means the positive and negative charges perfectly cancel each other out, leaving the object electrically neutral. It makes sense, right? Just look at your coffee cup, a pen on your desk, whatever it is, and they're not charging, they're not moving. They're just there because of that balance, right? So, static electricity will occur. You'll get that charge when a physical contact and friction rip electrons away from one object and they dump them onto another. Because the electrons cannot immediately move or flow away, they kind of like remain trapped and stationary. This is why we call it static, meaning they're staying still. Well, here is the secret weapon. Why do certain materials, right, cause static while others do not? The answer lies in the molecular property called, we're getting deep in here. You know why most of us don't understand all this, because now we're diving into areas like what? The answer lies in a molecular property called electron affinity. How badly a material wants to hold on to and steal electrons. Scientists rank materials on a scale called a triboelectric series. Tribopositive materials like human hair, wool, and even glass have a weak grip on their electrons and love to give them up. Tribo-negative materials, not positive materials, are like rubber, polyester, and amber. They have this appetite for electrons and love to steal them. So when any of these two materials from opposite ends of these spectrums touch and rub together, static electricity is guaranteed. This is exactly what's happening in your great science experiment all of us could do right now. You rub your hair against the balloon. What's happening? The human hair sits very high on the positive side of the scale, while the latex rubber of a balloon sits really low on the negative side. When you rub the balloon against your hair, the friction forces, this is all what it's about, the friction, forces the two materials into intense microscopic contact. The rubber balloon aggressively rips electrons right out of your hair. What happens? The balloon now is in excess of electrons, giving it a negative charge. Your hair has lost electrons, leaving it with a positive charge. Because like charges repel, your individual positively charged hair strands push away from each other. That's all of a sudden like why you look like Einstein, right? With your hair on end, right? And they're desperately reaching at the same time towards the negatively charged balloon, right? Now, here comes the key piece here. You may be thinking, why do some materials that I mentioned give up electrons and others attract them, right? That want them, that steal them? Well, this comes down to something that's fundamental in chemistry. It's called electronegativity and electron affinity. The behavior is driven by two main rules of atomic physics, and it's really simple to understand. Check it out. Atoms have a positive center. We've talked about this, the nucleus, and it pulls on the negative electrons orbiting outside, right? They stay together. But here's the thing. The givers, the large atoms like metals, have many layers of electrons. Their outermost electrons are sitting far away from the positive center. Because of this distance, the nucleus has a very weak, loose grip on them. They're easily stripped away, right? They move, in other words. The stealers are the small atoms. Their outer electrons sit very close to the positive center. Because the distance is so short, the nucleus exerts a powerful, tight grip on their electrons, and it acts like a magnet for any passing electrons from other atoms, right? So this desire for a full outer shell, the stability factor, the atoms are only stable when their outermost electron ring, right? They call this the valence shell. Stay with me. This is only stable, these atoms, when this shell, the electron ring, is completely full, which usually means holding exactly, believe it or not, 8 electrons. Materials with the outer rings are mostly empty. When they contain only 1 or 2 electrons, they find it cheaper, energetically cheaper, to just throw those extra electrons away or drop down to a stable lower layer. Materials whose outer rings are almost full, again, full being almost 6 or 7, there it is, 6, 7. It's amazing how often we talk about this. When they're full, meaning they have about 6 or 7 electrons, they aggressively are desperate to steal 1 or 2 electrons to finish their collection and establish this stability. So why are we talking about this? Because this has huge implications. This atomic tug of war that splits this physical world into 2 completely categories of matter. And it dictates how all of technology and our nature around us function. Why? Because it dictates conductors versus insulators. Because some atoms naturally let go of electrons, we can build conductors. Copper wires, we mentioned metals, right? They will transport the energy or the flow of electrons hundreds of miles. Because other atoms tightly lock down their electrons, we can build insulators. What are insulators? Like we talked, what are the electrons that tightly lock down and grab them? Well, like rubber. So our insulators, like rubber coatings, safely handle the high voltage power lines without getting electrocuted. What does this functionally also mean? It powers every battery on Earth. A battery is literally a controlled chemical boxing match between the giver material and the stealer material, right? You got positive and negative charges on batteries. We can see them on both sides. Inside a lithium-ion battery, the lithium atoms happily give up their outer electrons. Those stolen electrons are forced to travel out of the battery through your phone's processor to power it, your flashlight to power it, and it goes into a material on the other side that has an appetite to receive them. Bottom line, through all this, you can dive so far down a rabbit hole. Just know the basics, right? But at least hopefully I gave you the reasons behind the basics. And the basics are, in terms of electricity, the flow of electrons, you need something to conduct it, to move the electrons. And that's why you have metals. That's why you have copper, right? That moves the electricity, the movement of electrons from one place to another, right? And that's why you also have rubber, which is an insulator that stops the movement. That's why you have rubber around the copper wires to make sure that it doesn't escape. The electrons refuse to budge. They refuse to move because no electrons can move across rubber. It acts as this brilliant shield, and it traps the electricity where it belongs. That brilliant shield is known as an insulator. It insulates it. It stops the movement. Now, there are many people along the way, smart people who figured out, they saw this phenomenon of static electricity out in nature and they tried to figure it out. And one of them, early on in 1752, was, we know him, right? Benjamin Franklin. And what was it that he proved with his little key at the end of his kite? Well, he proved that lightning was just a huge form of static electricity, right? That was a huge development. Now, when they moved from the idea of just this burst of energy, static electricity, into current electricity, in other words, movement of electrons through metals, the best analogy I can give you is you can just kind of imagine a line of marbles inside a tube. You push one marble into one end, the marble at the other end pops out, right? And that happens immediately. Well, electricity behaves in the same way. The electrons push the other electrons. Those continually will move as long as you have that conductor. Well, here it is, where we made a giant leap around 1800. It was this Italian scientist, Alessandro Volta. Yep, there you go, Volta, right? This is where volts come from. He invented the first practical battery. For the first time, people could create a steady flow of electricity whenever they wanted. This was revolutionary. The electrical unit, volt, is named obviously after Volta. The battery era had begun. They were useful, but they were expensive. They were limited. Scientists wanted more. And now we're approaching the 1830s. A fellow by the name of Michael Faraday made one of the greatest discoveries in science. He found that moving a magnet near a coil of wire could create electricity. This discovery is called electromagnetic induction. It became the foundation of nearly every power plant on Earth. Here's the amazing part. Even today, 2026, when this podcast episode is released, most electricity is still made using Faraday's basic principle. Whether the source is coal, natural gas to generate energy, right? The goal is the same. You use this energy to spin a turbine. That turns a generator, that moves magnets near wires, and that produces electricity. I mean, at the very basic level, because this can be an entire podcast, what's actually happening when he actually discovered this, he had this stationary magnet inside this coil of copper wire. If it was just sitting there, it did nothing. But if he pushed the magnet towards the wire, what ended up happening was he sent a current rushing towards the wire. And then he pulled it back out. The current rushed in the opposite direction. What actually happened in this experiment? He proved that just by having magnets involved, you could instantly create an electric current. The magnet was the new piece. The magnet was magic, right? Because before the discoveries, batteries were the only way to move electrons, right? But they rely on small chemical reactions that quickly run out. His breakthrough, Faraday's breakthrough, was realizing that you could replace a human hand moving a magnet with a spinning wheel by hooking a copper coil up to a wheel spun by rushing waterfall, wind, or even burning coal, right? The steam that's produced. You could keep magnets and wires moving past each other forever. The spinning wheel turns the raw mechanical motion into a nonstop, infinite flow of electricity, allowing us, yes, to power not only our toaster, but entire cities, instead of a single light bulb with a battery. So now that we had this flow of electrons, we had this concept of electricity, along comes Thomas Edison in the late 1800s, and now he's actually creating light. He didn't invent the first light bulb. What he did was improve a lot of the designs and, the complete and complicated electrical system that could power homes and businesses and move it from one place to the other. The light bulb itself isn't very useful, right? You need power plants, you need wires, you need switches, safety systems, everything. He helped build that entire network. So while, yes, we always say, well, he invented the light bulb. Well, yeah and no, but he put everything together using electricity that now we've been able to understand. And clearly the first application of electricity is creating light at night. And this is what he enabled. Now, at the same time, there was another fellow by the name of Nikola Tesla. You may have heard of him as well. Well, he supported something called alternating current, AC. Edison supported direct current, DC. Yes, you can go back to my previous episode on Charles Steinmetz, who was a brilliant mathematician that worked with Edison and supported, along with Tesla, alternating current. DC basically is traveling in one direction, and it was limited in terms of electricity moving. You could only go so far, right? AC is like cars constantly reversing direction, right? AC had a huge advantage because it could travel the long distances more efficiently. And that's why AC won. Today, all the electricity coming into our home is AC powered, and we can thank Nikola Tesla and Charles Steinmetz for that. Now, how does electricity get into our homes? Well, you got first the power plant. It generates the electricity. Then you got transformers that increase the voltage, right, to go over all these long power lines. Think of it moving electricity from not only house to house, from city to city, right? A high voltage electricity will travel those long distances with less energy loss, right? That's why you need the transformers to increase the voltage. Well, then you have these huge transmission lines that carry the electricity. And then once you get down to, let's say, your home, you need substations that reduce the voltage. And then finally, you need the little buckets up on top of the poles. They're called neighborhood transformers, and they lower the voltage again, and the electricity eventually makes it into your home. So if you remember one thing from this episode, just remember this. Electricity is the movement of electrons. That's the core idea. A tiny spark from a doorknob, whether it's that or it's a lightning bolt going across the sky, whether it's a battery powering a flashlight or a giant power plant lighting a city, all of them are the same basic phenomenon, the movement of electrons, the movement of an electrical charge. It's this invisible force that humans have spent thousands of years trying to understand. It started with amber being rubbed against fur in ancient Greece, and then it moved many, many years up until Benjamin Franklin, and his experiments, to Volta and his batteries, to Faraday's and his generators, then to Edison and his lighting systems, and Tesla with his AC power grid. Well, all of this whole time period, electricity became some of our greatest achievements, and we wouldn't think about it without electricity and understanding it. We wouldn't have practically anything here in our modern world. We flip a switch and we expect lights, right? We plug this little plastic attachment into the wall, and then all of a sudden we have our phone that's charging, we have our computer that's turning on, we're watching our TV. It's the story of electricity. It's the invisible power that shapes everything around us. Friends, thanks for joining us, learning all about electricity. I hope you have a better understanding of it. Reach out to me at kevmok21@gmail.com. We have a Facebook group. We have a YouTube channel. Hit that plus button in the top right-hand corner to subscribe to the podcast. You get it automatically when new episodes are released. That's the best way to follow the podcast. And certainly, Love those ratings, love those reviews on Apple Podcasts. Can really help get the word out. Organically, it can happen by telling friends and family and neighbors, anybody in your life. But ultimately, reviews and ratings help as well. Until next time, have fun and keep learning.